But yeah, so I'm Kev. I'm a final year PhD student at the University of Leeds, and thank you all for having me. Before we get going, a quick shout out to my supervisors and collaborators as listed here. So that's Dave and Dan at Leeds, Simon at Iceland, Amde, who's at Brussels now, Yared at Ethiopian Electric Power, and Gezahain at Addis Ababa. So before we get going, I'd like to start by going off on a bit of a tangent. One of my interests is in the deep carbon cycle, which is the movement of carbon within Earth. Before I joined Leeds 3 years ago, I did some work with Sasha and the Deep Carbon Observatory on this subject, because different plate boundaries have different carbon outputs or inputs. So it's a whole range of different factors. We need to consider each individually when looking at how they affect the deep carbon cycle. So what I did was I combined our present-day understanding of CO2 at different tectonic settings, shown here at the top, with tectonic setting evolution modeling, shown here at the bottom, to see how total tectonic CO2 outgassing relates to atmospheric CO2 through geological time. And while this was a really interesting and fun study to be a part of, one key result that we had was this, which shows that continental rifts, shown here is this solid red line, produce a lot of volcanic CO2 relative to the other settings. However, there's also quite a bit of uncertainty, as you can see from the shaded area. So we need to know more about the rifting process if we want to understand how Earth's tectonic cycle and carbon cycle have co-evolved. In particular, what we want is a better understanding of sub-rift melt generation, as a large proportion of this carbon is expected to be magmatic in origin. And the reason for this overall uncertainty is due to poor understanding of the rifting process, which evolves both temporally and spatially, as Miriam just pointed out. And a good place to see this all in action is in East Africa, where the rift evolves from south to north. So there are those large border faults breaking in the Kenyan rift, where the deformation is focused along the flanks of the rift. And then as we move further north into the Red Sea, that's sort of like the terminal stage, this mid-ocean ridge, where now all the deformation is magmatic and focused in the rift center. My focus is on Ethiopia, which is this in-between stage showing the final moments of continental breakup. Understanding the magmatic character of the main Ethiopian rift allows a better understanding of advanced rift development, with further implications for understanding plate tectonics and therefore the deep carbon cycle. We therefore want to know more about how melts are generated in the mantle and stored in the rift crust. So this is the main Ethiopian rift over here, this poorly understood hybrid stage where extension deformation is now focused in the center of the rift as opposed to the flanks. Border faults are now inactive, and most extension is taken up by magmatic intrusion and intra-rift faults as opposed to just pure breaking of the large border faults. So how can we understand this interplay between melt generation and geodynamics better? Well, to answer such questions, we need to look at what's going on in the melting mantle where the magmas are being generated. Now, seismic tomography suggests the presence of this large-scale mantle plume, which is centered on Afar and extends to depth. We therefore know from geophysics that there is this thermochemical deviation of the Ethiopian mantle from normal mid-ocean ridge mantle, which is considered to be ambient mantle. And the role the plume plays in sub-rift melt generation remains somewhat enigmatic. S2P receiver functions, such as those here shown from Reichardt et al. 2012, suggest that the lithosphere-asthenosphere boundary, or the LAB, is absent underneath the rift, shown here on the right-hand side, but present underneath the plateau, so you can see the signal here on the left-hand side. In this case, melting continues to shallow pressures passively, like a mid-ocean ridge, and melt generation is therefore mid-ocean ridge-like. We would therefore expect shallow melting at the base of the crust. But it's since been understood that melt in the lithosphere can shield the lithosphere-asthenosphere boundary from imaging. We therefore need to rely on other methods that don't use geophysics just to double-check this. Enter petrology and geochemistry, which provides us a means to estimate temperatures and pressures of melting, as the chemistry of melts is affected by pressures and temperatures of melting. Major element thermometry, shown here on the left-hand side, suggests that mantle temperatures underneath Ethiopia are elevated. And rare earth element distributions from rift basalt, shown here on the right-hand side, agree. But they also furthermore have this heavy rare earth element deficiency, which is called a garnet signature. So heavy rare earth elements are less prominent in melts, which are deep, as they like hanging around in garnet, which are also present at depth. Therefore, if you melt in the presence of garnet, your resultant melt will have less heavy rare earth elements comparatively to those you get when you melt shallower. So that's why we have this slope in the heavy rare earth elements, or rather in this sort of trend between the medium to heavy rare earth elements on the right-hand side of this plot over here, which you don't really get when you melt at shallower pressures. And this all suggests that there is this plume-affected mantle present. But such methods often have a few caveats involved. They often assume a homogeneous mantle of a known composition, which is unlikely if a mantle plume is present. We would expect other more fusible lithologies, such as proxenites, to be present as well, maybe. A mantle of multiple melting and non-melting lithological components will affect the chemistry of lavas erupted at the surface. So illustrated here are the effects of changing proportion of a non-melting component in the mantle. And this has a direct effect on both the trace elements, shown here on the left-hand side, and the major elements on the right-hand side, as a result of affecting the thermal pathway taken by the mantle as it melts. So despite the same component, Al-in-olivine, melting in both cases, the final geochemical results are different because of these thermal pathway differences. So my research questions are as follows. Can we confidently determine Ethiopian mantle temperature and composition using petrology to complement what we know from geophysics? What is the depth of melting in the Ethiopian Rift Afar? And how does the Ethiopian mantle compare to ambient mantle in terms of its temperature and composition? While most previous studies often use iron and magnesium in olivine and glass as a thermometer, iron and magnesium in glass and olivine are both easily reset by diffusion. So here I've used the olivine spinel aluminium exchange thermometer. And the benefits of this thermometer is that aluminium is slow diffusing in olivine, and this thermometer is also independent of pressure, silica activity, and oxygen fugacity. Hence, the temperature we record can't really be easily altered post-crystallization. Olivine and spinel are also the first phases to form from mantle-derived melts. So olivine crystallization temperatures will fall near the basalt liquidus temperature, which will be the freezing temperature of your basalt. And the key thing about selecting these inclusions is that they have to be completely enclosed by the host crystal, otherwise there's a chance they'll get re-equilibrated. So my materials are from the Boku volcanic complex in the main Ethiopian rift, which I personally sampled in 2019, and also some samples from the Bahu in Afar, which were collected by Dave Ferguson for his PhD. And here are some olivines from the Boku volcanic complex here. So these olivines were picked from scoria, and they've been mounted in epoxy and polished. And they're packed full of bits and bobs, as you can see, especially this fellow over here on the left-hand side. These are mostly melt inclusions, but there are also quite a lot of spinels as well. Both phases here are analyzed by probe and then fed through that thermometer equation that I just showed you. And here are our results. So here I've plotted crystallization temperature against force-the-rate, which is a measure of iron-magnesium ratio in olivine. And this is what we get. So it looks like the main Ethiopian rift crystallizes cooler and Afar hotter, but there's also more scatter in the Afar distribution. At first glance, if we were to compare our results here to mid-ocean ridge basalts and large igneous provinces, we could suggest that the main Ethiopian rift is of a similar temperature to mid-ocean ridge basalts, just looking at the crystallization temperatures. However, we always have to keep in mind that we can't just consider mantle temperature to olivine crystallization temperature to be a direct link. Olivine crystallization temperature is just the end product of this melting process. We need to consider a lot of other things as well. For example, the conditions under which the mantle melts, that's controlled by the temperature of the mantle and also its composition. So be that lertzolite or maybe more fusible peroxenites, or even non-melting components all together, which affect each other's thermodynamics during melting. We also need to know where melting stops, which will be the thickness of the lithosphere, and we also need to know where crystallization begins, which will be somewhere around the base of the crust. And only by knowing all of these things can we predict the properties of crustal magmas. So what myself and a few other collaborators have done is we've developed this Python library for multi-lithology mantle melting, which can predict the thermal pathway of melting from the mantle and estimate olivine crystallization temperature by accounting for all of these different things together. And what our mantle melting model does is it takes up mantle composition, temperature, lithospheric thickness, and crystallization pressure, all of those things I mentioned before, into account, and then predicts the crystallization temperature of olivine and the thickness of generated melts from these starting conditions. And my contribution to this work has been an add-on which allows us to predict rare earth element concentrations as well, which is a function of depth owing to the garnet signature that I mentioned before. And in doing so, we set up this problem that can be inverted. So by running our forward model a vast number of times, we can obtain lots of data for the parameters on the right-hand side, which may or may not match what we observe in real life data. We can then find a combination of model parameters on the left that best fit the data on the right by plotting up probability distributions or our inversion solutions. And these inversions are performed using the multi-nest algorithm. However, for this method to work, we first need to establish whether or not our olivines are primary and have crystallized from mantle-derived melts. So the first olivines to form from mantle-derived melts are normally about force strike 91 or 90. And as you can see, our olivines are not at force strike 90, they're actually quite evolved, they're lower force strike. So what we need to do is we need to correct for this by finding the liquid line of descent, or the crystallization path, for olivines in order to estimate their primary crystallization temperature. So that's the temperature of the olivine as it crystallizes in equilibrium with a mantle-derived melt. The main Ethiopian rift in the top left is quite well constrained, so we're able to determine the liquid line of descent fairly straightforwardly, but the Bahu is not. So we need to try different temperatures to gauge the uncertainty in the temperature when olivine first crystallizes. On top of that, we can also use further constraints from rare earth elements. So here I've shown some from the Boku volcanic complex recorded by Amde Zafu Tades. And here you can also see that there's this deficiency in heavy rare earth elements compared to the medium rare earth elements that I mentioned before. So here we use lanthanum, dysprosium, and terbium ratios to describe the final shape of the rare earth elements and use those as our constraints. And we use ratios as opposed to absolute concentrations, as the absolute concentrations are affected by fractionation. We can also use melt thicknesses as a constraint. So we can estimate those from seismic profiles by calculating the difference between the true thickness we observe and a stretch factor. And this will provide us an estimate of magmatic thickness. So at the main Ethiopian rift, we'd estimate around 5 kilometers of melt or so. At Afar, it's close to 12 or 13 kilometers. So as for results, first I'll talk about the Boku volcanic complex in the main Ethiopian rift, and then I'll move on to the Bahu, which is in Afar.
You've had 10 minutes now, Kev.
Cool. So on the left-hand side, what I've got is a cross-section through the crust and the uppermost mantle. The lithosphere remains thick for now, at about 50 kilometers, and the crust mantle boundary, the MOHO, is shown here in red, and that's at about 30 kilometers or so. On the right-hand side, what I've got is an illustration of the different probability distributions that are returned by our inversions. So mantle temperature, which is this value up here in the upper right, is hot relative to mid-ocean ridge basalt mantle, which is at 1350 degrees C. The mantle composition is shown here in this ternary plot, and it's plotted between lertzolite, which melts, proxenite, which is like cheese. It melts a lot more than lertzolite, and harsbergite, which is a non-melting component. And what we can see here is that compared to mid-ocean ridge basalt, which I've plotted in a similar manner, you can see that the Ethiopian mantle is more enriched, or we expect it to be more enriched in a more fusible, easily melted proxenitic component. This median composition, which is shown by this orange dot, produces this rare earth element distribution when we feed it through our pi melt forward model, which matches fairly well with the melts we observe. So that's a useful sanity check to make sure that our inversion works. Moving on to Afar, we can see that there are two key differences. The first one is that the lithosphere-asthenosphere boundary is now significantly thinned. So our lithosphere is thinned. The median is now sat at around 30 kilometers, which is much thinner than the main Ethiopian rift, which is at 50 kilometers. And furthermore, the mantle is much more enriched in proxenite, which is itself more so enriched than the main Ethiopian rift, which is itself more enriched than mid-ocean ridge basalt source. Again, the median inversion solution, which is shown here, is this orange dot in our ternary composition plot and falls within the observed values, matches quite nicely. Our potential temperature is fairly similar to that of the main Ethiopian rift. So why is there this difference in mantle composition and lithospheric thickness? So this comes down to the melt thickness requirements we put on our model. So in order to match the increased melt volumes observed at Afar, we need to make sure that more melt is produced. Therefore, the lithosphere-asthenosphere boundary is shallow to allow for more melting. Here I've plotted up some melt fraction curves, which are split between the total melt fraction, shown here in green as the solid line, and the contributions from the two melting lithologies, lertzolite and peroxenite. You can see here that the Spinel field at about 100 kilometers or so, by the time we even get there, about 50% of our peroxenite has been melted. So the garnet signature predominantly comes from this deep peroxenite melting. So that's how we can get this garnet signature without unnecessarily thick lithosphere. Where does this peroxenite come from? Well, it's probably linked to the position of the Afar plume, but we need a bit more key geochemical information on that to confirm it, mostly from primitive rift basalts from both the MER and also Afar. Now, if we compare the potential temperatures to other settings, calculated using the same approach, we can see that the main Ethiopian rift and Afar fall somewhere between mid-ocean ridge basalt source and Iceland. So this could suggest that there are tiers of plume, but we've already made quite a lot of assumptions in our model already, so I wouldn't go that far. However, we can say that the Ethiopian mantle we would expect would be distinctly elevated in temperature compared to mid-ocean ridge basalt source. So to conclude, we developed a model which can allow us to predict olivine crystallization temperatures, melt volumes, and rare earth element concentrations from mantle conditions. The Ethiopian mantle is elevated in temperature compared to ambient mantle and also more enriched in feasible peroxenite. And the main differences in melt generation between the main Ethiopian rift and Afar can be attributed to comparative depth of melting and enrichment in mantle lithologies between these two different localities. Now, the next steps for me will be to look at melt storage in the crust. And while I won't be going into any more detail about this because I'm running out of time, this is just a preliminary plot I've made using some volatile data to determine pressures of melt storage. So this story will be saved for another day, I think. And as a final slide, here is a graphical abstract for this work, which I've just submitted, which I'm quite happy with. And yeah, thank you for listening to me, and I'm happy to address any questions.
Thanks, Kevin. Sorry for dropping it for a minute there. If anybody has any questions, you can either put Q in the chat or ask it directly. I'm kind of curious, that's quite the inverse problem. You've got a lot of free parameters in there. Which do you think you have the greatest uncertainty in terms of the inputs of that inverse problem?
I'd say, so Mantle source composition, definitely. So what we've done is we've run a load of different Mantle source compositions. If you look at some of those figures that I've just shown you, which I can quickly hop back to, you can see that the Mantle source compositions we used were primitive Mantle from Sun and McDonough for lertzolite, and for Broxenite, it's a 50-50 mixture of DMM from Workman and Hart and mid-ocean ridge basalt. So this is where most of our uncertainty would lie in understanding what the composition of the mantle is. So in order to account for that, what we've done is we've run the same model again, but for different mantle compositions, and they all return fairly similar potential temperatures and lithosphere, asthenosphere boundary depths. So I think that's where most of the uncertainty would lie, but it would be worth looking into more primitive or perhaps parental magmas from this region just to see whether or not we could put a bit of a better constraint on that.
Cool, thank you. There's a question in the chat from Ritska.
Okay.
Yeah. Hi, Kevin.
Hi.
Nice talk. I was wondering about your potential temperature estimates. I mean, can you comment on how robust and how much you trust the absolute values and what the uncertainty of the absolute values is? I mean, do you have any playroom? Yeah.
Yeah, so these potential temperatures I've recorded in the figures up here. Those are the median temperatures from our inversion solutions with a 95% uncertainty interval. So I think in one of the final figures over here, you might have noticed that these are fairly well constrained compared to everything else. And this is mostly due to that rare earth element constraint that I've written for Iceland and for the mid-ocean ridge basalt. What we've done for that paper is that we've used the proportion of peroxenite we know to be present in the mantle at these two locations. For Hawaii and large igneous provinces such as Peru, we don't really have that benefit. So hence the potential temperature there is quite a lot more less constrained. As for the main Ethiopian Rift and Afar, they're fairly nicely constrained for both the models I said before that I've run with a more depleted mantle composition compared to these. So we're fairly happy with how these temperatures have come out.
Yeah,
course,
I think I'm not so much questioning or that there is a variation of potential temperature between these areas, but I'm more wondering how robust is your absolute estimate. For example, Hawaii having a potential temperature somewhere between 1550 and 1600 degrees C. I mean, could that be? I mean, we know it's hotter.
Yeah.
But how confident are you with the actual absolute value?
The absolute value is as in the median of these inversion results, or
well, for instance, I mean, could you explain the amount of melt in at Hawaii with a lower potential temperature? I mean, do you really need about almost 1600 degrees C? I mean, we've used very simple decompression melting models, and the next speaker will show some results from that.
Mm-hmm.
If you use very simple decompression melting models, going back to, I don't know, Mackenzie and Bickel and many others, 300 degrees C is really enormous. It will give you an enormous magmatic thickness. Mm-hmm. So I'm just wondering where these absolute values are based on.
Yeah, so these absolute values will just come down to the PyMelt module that we've been using to run all these. So we've had to reparameterize a new value with lertzolite and some new peroxenites, and all of these combined together will melt together to produce these crystallization temperatures that we observe. So I think for Hawaii, what we did was, rather than use a sort of triangular melting region, we used sort of like a fairly simple one-dimensional plume conduit. And that is only constrained by the buoyancy flux on Hawaii and also the crystallization temperature, which is why the uncertainty on it is so large. I feel like if we had better constraints on it, then maybe that would bring the temperature down a bit. But as I said, this is just a 95% confidence interval and the median. So the true value could lie somewhere within that bar. But this is just simply the results of what we get from our method. It was to show that the crystallization temperature, if we just consider it by itself, is not necessarily that well of a constraint to constrain our Mantle potential temperature. We need to consider a whole host of other things as well.
Right, thanks. That's okay.
Okay.